Some of you have been asking why we even have to do logarithms, like what's the point? Well, hopefully this will give you some idea why they are helpful. Um, in this case, we're going to be looking at solving exponentials. Now, it may be funny that I start talking about logarithms when we're solving exponentials, but as you'll see, it turns out we need logarithms in order to be able to solve exponentials. So let's consider this problem, and hopefully this will help illustrate it for you. If we use the normal interest formula for compounding continuously, A equals PE to the RT, and we consider this question. Pilkington invested $1,000 in an account for 30 years. The account earned $12,000. What interest rate was he getting? Okay, well let's plug in what they've given us here. It earned $12,000, so we'll put 12,000 in for A. He put $1,000 in initially, so that's our P. It asks what the rate is, so we need to find R, and it says the time is 30 years. Alright, now you may be saying, well, how could he not know the interest rate he put his account in for? Okay, that's a fair question, but a real world question may be something more like this, where they're saying, okay, I have $1,000 to invest now. I want it to become $12,000 in 30 years. What interest rate do I need to get in order to obtain that goal? Okay, so to do this, we need to solve for r. Now this is different because r is in the exponent, and that makes it harder to solve for than normal. So this is what we have to do. We want to first divide both sides by 1,000. That gives me 12 equals e to the r times 30. And now we need to get rid of that e, so you've got to think about logarithms. What cancels out an e? Well, natural log cancels out e. So on the right side here, natural log of e cancels out, leaving me just r times 30. So I have natural log of 12 equals r times 30. Now if I want to solve for r, I just divide both sides by 30. So I get natural log of 12 over 30 equals r. So we can plug that in our calculator. Make sure you close those parentheses around the 12. We're not natural logging the 30, just the 12. And we get 0.0828. So about 8.28% would be the interest rate that he earned to get that amount of money. So what natural logs and logs in general allow us to do is to solve exponentials. They give us a way to get variables out of the exponent, because it's really hard to solve for them when they're in the exponent. So this gives us a way to get them out of there. Okay, so here's just a simple problem. Solve 4 to the x equals 15. So one way to do this, and I'm going to show you two ways. One way to do this is to take the natural log of both sides. Now, if you remember the properties of logs that we talked about, one of the properties says that we are allowed to take exponents and move them down front as coefficients. So again, what logs allow us to do is get the variables out of the exponent. Now we can just divide both sides by the natural log of 4, and I get x equals the natural log of 15 over the natural log of 4. And we can plug that in our calculators. We get 1.953. So we'll just call that 1.95. And it would not be possible to solve these without logarithms. Logarithms are the only way we can do this. Okay, now let me show you one just alternate method. Both of these work. You can kind of go with your preference most of the time. But if you remember, one thing we learned to do was convert from logarithms to exponentials. So if we start back up top here at 4 to the x equals 15, we can convert that into a logarithm. Just remember log BAP. Log, base, answer, power. So this is another way that this gets you out of the denominator. Excuse me, not the denominator, out of the exponent. Gets your variable out of the exponent. Because we can plug log of base 4 of 15 in our calculators using the change of base formula. Remember, we can just write that as log of 15 over log of 4, which is the exact same thing. If you notice, we're pretty much plugging the same thing in. We just use natural log one time and common log the other time. And both of those work as far as the change of base formula is concerned. So that just gives us 1.95 again. So you can do that one either way. I will probably tend more towards the first way. I think it tends to keep things simpler and more uniform across all types of problems, but that doesn't mean you can't do the way I've done in red. So if you like that and you want to try that out, feel free. Okay, solve 5 to the x equals 134. So again, my recommended way would probably be to take the natural log of both sides. Bring the x down front. That's a property of log that allows you to do that. And then divide both sides by the natural log of 5. I never do seem to have the calculator on the side I need it to be on, so sorry about that. Let's see, natural log of 134 over the natural log of 5. 3.04. Alright, next up, 40 times e to the 0.06x, 0.6x equals 240. Alright, now if you have a coefficient in front, you don't want to take the natural log yet. You need to get the coefficient moved out of the way first. So I'm going to divide both sides by 40 here, and get e to the 0.6x equals 6, and then take the natural log of both sides. Well, the nice thing when it's e is natural log just cancels out the e, so I get 0.6x equals the natural log of 6, and then just divide both sides by 0.6. So let's see what this will give us. Natural log of 6 over 0.6, and we get 2.99. Alright, so this one's a little bit different, and this is one where I personally feel like it's going to be a little easier for you to do it the way the method I've been using, but it still will work if you use the log BAP way and just convert it to a log. But let's do this right now, and we'll add 3 to both sides to start with. And then I'm going to get the natural log of both sides. That will allow me to move this entire exponent out front. You should put parentheses around it though, because you're multiplying by the whole thing. Now I need to divide both sides by natural log of 5. So I get 4x minus 7 equals the natural log of 13 over the natural log of 5. Now if you want to go ahead and plug that natural log in your calculator and then get a number, you certainly can. There's nothing wrong with that. I usually leave it because then I can make sure I get the exact answer and I don't end up rounding before I should. So my next step would be to add 7 to both sides and then divide both sides by 4. So I'll have something that looks like this. Natural log of 13 over natural log of 5 plus 7, all divided by 4. So in my calculator, I'll just do that in a couple steps. We'll first do the natural log of 13 over the natural log of 5. Then I need to add 7 to that. Then I need to divide by 4. So by waiting till the end to plug it in my calculator, I made sure I didn't have any rounding errors by rounding early on. Now I have the exact answer, and I know if I'm rounding it now to 2 decimal places, my answer would be 2.15. So x equals 2.15. Alright, so here's another type example you might see. R equals 6e to the 12.77x, where R is the percent risk of an auto accident, and x is the blood alcohol level. What blood alcohol level would lead to a 17% chance of an accident? Let's put a question mark there. There we go. So we're told that a 17% chance, and we're told to find x, which would be the blood alcohol level. So we'll plug in 17 for R, and then solve for x. Okay, so I need to start by dividing both sides by 6. You cannot take the natural log while there is a coefficient in front. You've got to move that coefficient. Okay, now I can take the natural log of both sides. That gives me natural log of 17 over 6. And then natural log just cancels out the e, so I get 12.77x. And then I divide both sides by 12.77. So the natural log of 17 over 6 divided by 12.77. And so we get 0.0815. So we'll just call it 0.08 for the blood alcohol level. So a relatively, well, I don't know if it's small or not, actually, to tell the truth, but a 0.08 alcohol level will lead to a 17% chance of an accident. Seems pretty serious to me. So anyway, that's how you solve exponentials. So again, the idea here is we're going to use logarithms, particularly the natural log, in order to bring things out of the exponent and down front where we can use them.